Welcome to Learn America's Regents Review for Algebra 1. We're here today for a 2-hour session, and we're going to be covering the following topics: sets of numbers, square roots, algebraic expressions and writing equations, solving equations, applications, and lots of word problems, which are mostly Regents questions. And then we'll take a 10-minute break, and then we'll do a section on monomials, polynomials, exponents, and factoring. So let's get started. First thing we want to do is to talk about the different sets of numbers. There are sets of numbers that you've learned when you were younger. The first thing you did was you probably learned how to count, and those were called the natural or the counting numbers, starting with 1, 2, 3, and so forth. And then we included the element 0, which then became the set of whole numbers, which you probably are familiar with, and that's represented by the letter W. And then we have the set of integers, which are denoted by Z, and those are the positive and negative whole numbers and 0. And then we have the set of rational numbers, and these are in the form of P over Q. So all of your fractions are rational numbers, all of your decimals, all of your repeating decimals are all rational numbers. And these can be written in the form of P over Q, where Q cannot be equal to 0. And even if you have a number such as 8, you can write that as 8 divided by 1. If you have a decimal like 0.1, you can write that as 1/10. All right, another set are the irrational numbers, and you'll notice that if it's rational, it can be put in the form of P over Q. The irrational numbers cannot be put into that form, and we call that Q bar, which basically is the complement of the rational numbers. The set that contains both the rational and the irrationals are the real numbers, and that's denoted by R, and sometimes it's just a plain script R, sometimes it's a very flowery R, and together with the set of imaginary numbers, they make up what they call the complex numbers. The empty or the null set is denoted by the brackets with nothing inside or the null set. Please make sure that you don't put a 0 inside the brackets thinking that that's your null set, because that will look like it's the set containing the element 0, and it has a completely different meaning. The universal set is denoted by U. So here's sort of a Venn diagram of the set of numbers that we're looking at. The complex numbers is the largest set. These are made up of the real numbers and the imaginary numbers, which we haven't gotten to yet. You'll learn about those probably next year. Then we have the real numbers that are broken up into the irrationals and the rationals. And then a subset of the rationals are the integers. A subset of that are the whole numbers, and a subset of that are the natural numbers. Okay, so this is our first Regents question. It says, given the following expressions, and you have 4 choices, which expression results in an irrational number? You want to take a minute or two and see if you can do that? Let me know when you have an answer.
I can't see. I can't see.
Can you put a light on? Okay.
But how do you put in what you should do? This fraction.
Right, Daniel, one thing you might notice is that if you have the sum of 2 fractions, which are both rational numbers, can you combine those into one fraction? So you know that that actually has to be a rational number. All right, if you look at number 2, you have an irrational number 2, radical 2, and that can't be simplified. So I know right away that's my irrational number. Then if we go into choice 3, you'll notice radical 5 times radical 5 is the same thing as the radical 25, which can be simplified into 5. And I can put that in the form of 5 divided by 1, which makes it a rational number. And then what about the square root of 49? What's that equal to? 7, right. So 3 times 7 is...
That's a rational number.
Right, that's a rational number also. So the answer on this one is, in this case, choice number 2, 1/2 plus the square root of 2. That's the only irrational number. Okay, you can use calculators on that also, but you don't even have to figure that out with a calculator. All right, now order of operations. How many of you have heard about Please My Dear Aunt Sally, or PEDMAS?
I have.
Okay, and what does the P represent?
Parentheses.
Parentheses. The E represents exponents, multiplication, division, addition, and subtraction. Now actually when I write this, I do it a little bit differently. I do the P and the E, and then I do the M and the D one on top of the other, and then the A and the S on top of each other, because the multiplication and division are done simultaneously, reading from left to right. The additions and subtractions are done simultaneously, again reading from left to right. So here we have an example. If we have 21 minus the quantity 2 minus 2 squared, this tells me, according to PEMDAS, that I want to do what's inside the parentheses first. So I'm going to simplify that and make it 3. So this becomes 21 minus 3 squared. Then I'm going to take the 3, since that's the exponent and it's squared, I'm going to do that second. So it's 21 minus 9. And then finally the subtraction, giving me a result of 12. The answer is 12. Okay, so now let's talk about simplifying radicals. In this case, we have the index. Most of the time, if you don't see a number up there, it's assumed to be a square root. Hi. And the number underneath the radical sign is called the radicand. List of perfect squares, and I always find that it's helpful to list the perfect squares on the side of my paper before I start simplifying radicals, and I'll show you why in a minute. So I list the perfect squares. I have it up to 15 squared, and now what I'm going to do is to see how I might simplify the radical 75. So I'm going to look for a perfect square in my list over here that might be a factor of 75, and I find that 25 times 3 is the same as 75. 25 is my perfect square, which becomes then 5 radical 3. Okay, you're welcome to take screenshots of these rather than taking notes if that's easier. Okay? Okay, now the next one over here, 2 times the square root of 48. A lot of people start looking at 48 and they say, well, I know that 4 is a factor, and that's great. But then if you break that up into 4 times 12 and you simplify that, then you're going to find that the square root of 12 can be simplified again. So you've got double steps. So what I do is the following, and you might find this is a really easy way to figure out the largest perfect square factor. I go back to my list of perfect squares, and I notice that 48 lies between 36 and 49. And then what I'm going to do is to work my way backwards, and I ask, is 36 a factor of 48? No. Is 25 a factor of 48? No. Is 16 a factor of 48? Yes. And that's the biggest perfect square factor. So now I'm going to break up 48 into 16 times 3. 16 is my perfect square. That comes out in front of the radical sign as 4, and then I have 2 times 4 giving me 8 radical 3 as my final result. All right, so look for the largest perfect square when you do these. Okay? Now, multiplying radicals, you have to make sure that they have the same index. So, for example, if you have no index written down here, it's assumed to be a square root. Same thing over here. This is a cube root because the index is 3. This is a cube root, the index is 3. And these can be multiplied together. But now if I look at this one, I have 2 radical 2, which is a square root, and I have a cube root. Those have different indexes, so I can't multiply them. So now let's see what we're going to do over here. What property will I use to go through the multiplication? What property am I going to use, do you think? Distributive, good. So this now becomes 4 radical 5 times 3 radical 5 plus 4 radical 5 times 2 radical 2 by the distributive property. Now what I'm going to do is to multiply the numbers out in front of the radical first, then I'm going to multiply the radicands. So it becomes 12 radical 5 times radical 5. Here I have 4 times 2, which is 8. Radical 2 times radical 5 gives me the radical 10. The radical 5 times itself becomes 5. So I have 12 times 5, which is 60, plus 8 radical 10. And I notice now that 10 is simplified as much as possible. There are no perfect square factors. So that's all I can do with this one. Okay? Adding and subtracting radicals, what you have to make sure of is that you have the same radicand, aside from the same index. You need to have a square root, or you have to have a cube root for both of them. And you'll notice here that, yes, they are square roots, but you'll have a 2 as a radicand and a 6. These cannot be combined, only if you have like radicands. All right, and then you'll notice over in here the addition property. If you have a radical x plus b radical x, you can add the numbers out in front and multiply the sum by radical x. Subtraction is basically the same thing. So now let's try this one. You have 4 radical 5 plus 6 radical 5. So you can simplify that into what? 10 radical 5, good. And then 8 radical 5 minus 3 radical 5. It's 5 radical 5, and then you want the sum, so it's 15 radical 5. Okay? Okay, this is a Regents question. Everything that has the little blue polka dots in back are Regents questions. So let's try this one. Given L, M, N, and P, which expression results in a rational number? Remember, rational can be put in the form of P over Q, where Q is not equal to 0. So let's give this one a try. I'll give you a minute to try it. Okay, how are we doing? Shall we take a look?
No.
Okay. All right, what do you notice about N and P while we're waiting for people to finish up? What do you notice about N and P? Right, they're both rational numbers. They're both perfect squares. So N is really equal to 4 and P is equal to 3. So that might be a good clue as to what would be the rational number. So let's take a look. How many of you have an answer? All right, let's take a look. All right, so now if you'll notice, see what I said? N and P became 4 plus 3. When you add that, you get 7. That's rational. In this case, choice A, you have an irrational which you can't simplify. The same thing with choice B and with choice D. Okay, so without even working through a lot of the problems, I can take a look at the original numbers and see if I can simplify from there. Okay, division of radicals. Now there are a lot of different problems that you can have with division, and each one sort of requires a slightly different approach. And you'll notice on this first one, if you have A divided by B, that's the same thing as the square root of A divided by the square root of B. Sometimes you can simplify the fraction. This one, however, you'll notice has 2 terms in the numerator, 1 in the denominator, and you have to divide each of those terms by 3 radical 3. And fortunately, you'll notice that 3 radical 3 divided by 3 radical 3 simplifies to 1. And here, the radical 3's will divide out, leaving me with 4/3. Then if I change this to 4/4 plus, or 3/3 plus 4/3, that gives me 7/3. And you must remember again that the index must be the same for the radicals. Okay? When a fraction contains an irrational denominator, which is what we have here, 2 plus radical 3, we have to multiply by something very special. And do you know what that's called? You multiply by the conjugate, C-O-N-J-U-G-A-T-E. And the conjugate of 2 minus radical 3 is 2 plus radical 3. So what we're going to do is to take 2 plus radical 3 and multiply it by the conjugate. Now, I'm multiplying the numerator and the denominator because this really is equal to 1. So I'm not changing the value. 1 is a multiplicative identity element, so I keep the same thing. Then using my distributive property in the numerator, I have radical 3 times the quantity 2 minus radical 3. And the beauty of multiplying the 2 conjugates down here is that when I multiply the first times the first, I'll get 4. If I take the inner product and the outer product, they're opposites and they add out to 0. So I've gotten rid of that radical. And then radical 3 times radical 3 is again the minus 3. And then simplifying, I'll have 2 radical 3 minus 3 divided by 1, which is simply 2 radical 3 minus 3. Okay, good to go? Okay, now here is a division problem. This is a Regents question. Let's take a minute and try this. You want to find out, again, which one is a rational number. Which one is a rational number? So the first thing I might look at is to see whether or not there are any perfect squares, similar to that last problem. Do you notice anything? Do any of those simplify into rational numbers? Let's look at 1 over the square root of 4. What's that really equal to? Go ahead. Good. And how about 1 divided by the square root of 9? Good. So if you have 2 rational numbers and you add them together, what are you going to get?
Irrational.
A rational number, great. So you don't even have to worry about, in this case, simplifying either of these and going through the work of trying to add them together. So let's see. Well, that's exactly right. The P plus W, choice 2. And you'll notice the work that you have to go through in this case by substituting in and then trying to combine. So this is where you can use a little bit of foresight in trying to answer the problems. Use some of those little clues along the way that really make it easier. Okay, for algebraic expressions, first of all, you have to look for what they call like terms. And go ahead. Terms are like terms if they have the same base and the same corresponding exponents. So for example, here you have a 2x squared, and looking over here, there's a negative x squared. If I don't have a coefficient in front of the x squared, what does it assume to be? How many x squares do I have here? 1, right. So this becomes 2x squared and a negative 1x squared. Those are like terms. Pick out the like terms over here. 2p and 5p. And here I have a 4b and the negative 15b. Becomes a subtraction operation, but if I look at the term, it's a negative 15b. All right, now for simplifying, what I'd like you to try now is to think about using the distributive property and then combining like terms. So if I distribute the p over the quantity 2p plus 4, that becomes 2p squared plus 4p. And then I have plus twice the quantity of p squared plus 5, becomes 2p squared plus 10. Group the like terms together, add them, add just the coefficients out in front. You have the base of p, the exponent of 2, and the coefficient of 2. And you've got a 4p squared plus 4p plus 10. And then since each of these are even numbers, you can factor out the 2 if you want. Okay?
Do you have to?
No, not necessary. Sometimes they'll give you, in the Regents choices, they'll give you a question that actually is in this form. Sometimes they'll take it down to this form. So just be on guard that you necessarily might not have to factor out that 2. That might be done along the way. Okay, here's a typical Regents question again. Take a minute and see what you can do. And this particular question is one of their favorites because look what's behind that binomial. It's a minus, so you have to subtract everything inside the parentheses. And this is where a lot of people get kind of tripped up because they don't remember that they are subtracting that 3 as well. Okay, do we have an answer yet? Go ahead.
D.
Say it with confidence, right?
D.
That's what we're here to make you feel, is confident and feeling good about all of this. So let's see, the correct choice is D. Terrific. Okay? So in this case, tell us what you did.
I distributed the 2 to 3g minus 4.
Good.
And then I got 6g minus 8. And then I put a 1 in front of the second pair of parentheses.
Great.
And I ended up with 6g minus 8 minus 8g minus 3. And then I combined 6g and 8g and negative 8 and negative 3.
Good. Nice job. Everyone agree?
Mm-hmm.
Okay. You got to feel really good when you go into that test. Okay. Now writing equations. This is something that a lot of people always say, I don't like equations, I don't like word problems. Well, we're going to get you over that because we've got lots of examples. I'm going to show you some easy ways of setting things up. So first of all, you'll notice that the statement versus an equation, the difference with a statement is that you don't have an equal sign, or you don't have like an inequality where you don't have a less than or a greater than kind of symbol. So the sum of a number and 14 is equal to 18. That's the statement, and then the equation a plus 14 equals 18. And you'll notice that the word is my clue that putting in the equal sign. So the one side, the sum of a number and 14 is the left, equals 18 on the right. Right? Twice y decreased by 8, so it's 2y minus 8 is equal to 2. And then the difference of a number and 12 is equal to 4. So we're going to say that b is the number and we're putting in the difference of 12, and the final result is 4. Now the formula is one that is a generic type of equation. It works for all squares. So the perimeter, for example, is equal to 4 times A. The area of any rectangle is length times base, or base times height. Okay? Now here's one Regents question again, typical cell phone plan. So I'd like to read this through. Has a fixed base fee that includes a certain amount of data and an overage charge for data used beyond the plan. A cell phone plan charges a base fee of $62. So that's a critical number, and an average charge of 30 per gigabyte of data that exceeds 2 gigabytes. So that first 2 gigabytes is included in that base fee of $62, and you're going to pay for anything that's over those 2 gigabytes. C represents the cost, and G represents the total number of gigabytes of data, which equation could be used to represent the plan if more than 2 gigabytes are used. So where are we going to start on this? If you just get your cell phone, what are you going to pay regardless of how often you use it? How much are you going to pay? What's the base fee? $62. Right. So I know I have to start with the $62. This 30 represents the charge per gigabyte over the original 2. So I know I have to have the 62. That takes out A and B as my choices. Now in this case, is G greater than 2 or is it less than 2? G represents the total number of gigabytes of data that they've used. And that's above what they originally had purchased. So the G has to be greater than. So to find out the difference between the first 2 gigabytes and what the total number is, we're going to take the G minus 2. So if I use 10 gigabytes and I got the first 2 in my original base fee, how many will I have to pay overage for? How many gigabytes will I have to pay overage? I was covered for 2, but I used 10. So I have a total of 8. And if you run into a problem and you're not sure whether or not to make it 2 minus G or G minus 2, put in a numerical example. You've got 2 gigabytes to start with. You've used 10. How do I find my overage? So it's going to be the 10 minus 2 or the G in general minus 2. Daniel?
D. I started with D.
Okay? Okay. So let's take a look and see what they're doing in this case. The G again is greater than 2. Number exceeds is G minus 2, and it's $30 per extra gigabyte. So the total cost is the base fee plus the overage charge. Okay? Regents exams love word problems. This is another word problem, and they give you a chart this time. It says a parking garage charges a base rate of $3.50 for up to 2 hours and an hourly rate for each additional hour. The sign below gives the prices for up to 5 hours of parking. Now, it says which linear equation can be used to find X, the additional hour parking rate. And they give you 3 equations. What do you notice about the left-hand column?
Goes up by 1.
They're all increasing by 1. What do you notice about the change in each element in the right-hand column?
Okay.
Daniel?
Okay. What's changing in the right-hand column?
How much does it increase by each time?
550.
$5.50. So that must be what the additional hourly rate is. So now, here's what we can do. It says which linear equation can be used to find X, the additional hourly parking rate. So what we're going to do, it says that the rate you just told me increased by $5.50 per hour. So what I'm going to do now is to take the choices that they gave me, and I'm going to take the first equation. I'm going to solve for X because that's the hourly overlay rate. And here I get X equal to 367, but you told me that the increase or the hourly charge was $5.50. So that one's out. B, solve for X. The X value here is $3.14. Doesn't match with what I need. C, when I work this out, yes, I get the $5.50 rate per hour. That's the one I'm looking for. But you always want to make sure that you check the remaining examples to make sure that you haven't made a mistake in your calculations. Okay, don't stop when you get that answer. Try the last one as well. Okay, solving equations by combining like terms. We talked about simplifying algebraic expressions. And again, with the distributive property, we're going to use that over here. And the idea would be to get all the terms that are like on one side of the equation. So here I have a negative 2x, I have a 3x on the right, and a negative x. I'm going to use the inverse operation to bring them over to the left-hand side. So if this is a positive 3x, I'm going to subtract. If this is a negative x, I'm going to add. And then while I'm at it, well, we have a plus 6 over here. I'm going to subtract that and bring it over to the right-hand side. When I combine the like terms, I have negative 4x equals negative 12. Divide by negative 4, and I get x equals 3. Okay? Solving equations containing parentheses. All right, same thing using a distributive property. When you remove the parentheses, you want to combine your like terms on the left-hand side and on the right-hand side. And then you're going to get all the terms with x on one side, all the terms with the constant values on the right-hand side, and here we have x equals 6. Okay? All right, so now here's an equation for you to try. Okay, here's a Regents question. Okay, which value of x satisfies the equation? All right, a couple of ways you can do this. You can take your 4 answers, if you like. You can substitute in for x. Using your calculator, you can back work the problem and see which one might check. Or you can actually just take the left-hand side, distribute the 7/3, not on. Not on. Is it not on? Yeah, it's on. Okay. Okay, how'd we do?
Good.
Okay, let's give it a try and see. All right, so on this one I chose to multiply or multiply through by 3. I want to get rid of that fraction. I'm not crazy about fractions. So when I looked at the original problem, I had a 3 in that denominator. And what I decided to do to make life easy was to multiply through by 3. And that now became 7x plus 9/4 equals 60. And again, I have this fraction. Don't like fractions, so let's get rid of it. Your LCD is 4, so if I multiply both sides of the equation by 4, I have 28x plus 9 equals 240. Subtract 9, divide by 28, and I get 8.25, which was choice A. Okay, fortunately, if you had taken the answers and started substituting in, you would have found that A was your correct choice. Okay? Okay, graphing solution on the number line. In this case, you want to make sure that depending upon what your domain is or the values that you have to choose from in your original problem, you may only end up with, in this case, a specific set of numbers, and you're going to darken those in on the appropriate number line. If you have x as an integer and you're talking about -4 less than or equal to x less than 2, you'll notice in this case that x could equal -4. So that's going to be colored in solid. Then you have -3, -2, -1, 0, and 1. 2 is not included because I don't have any equality. I just have the inequality in this case. All right, if it's a real number, there's a little bit of a difference because I'm talking about all the fractional values and all the irrationals and rationals between these two values. And if I have -4, I'm going to put a solid circle on -4. Everything on that segment is included. And then I'm going to get up to 2. This actually should have an open circle on 2. This one should be extended through 1. There should be a change on that one. All right, so it should go and have an open circle on 2. Okay, now, a lot of people are not crazy about word problems, but there are certain things that are very sort of standardized. And we're going to look at a number of different applications. All right, so first of all, let's start out with a class. You have 40 students in the class. The number of boys is 7 more than twice the number of girls. So which one is independent of the other one? Girls or boys? The boys are defined in terms of the number of girls. So the girls is the independent variable. And if I know the number of girls, could you then determine the number of boys? Okay, so we're going to start out by labeling our let statement. X is going to represent, Okay, let's see. 40, x is going to represent the number of boys in the class, and then 40 minus x represents the number of girls in the class. And it says that the number of boys, x, is equal to twice the number of girls and then increased by 7. So in this case, they decided to use x as the number of boys, where I maybe would have changed and done x as the number of girls. Using your distributive property, you'll have 7 plus 80 minus 2x. You're going to combine your like terms by bringing 2x to the left-hand side using addition. So I have 3x equals 87, combining the 7 and the 80, and then dividing x is 29. So we have 29 boys in the class, 11 girls in the class. Okay, here's a word problem. We're going to go through a whole group of different kinds of word problems just so you can kind of get a flavor of how to approach these. So we have Sam and Jeremy have ages that are consecutive odd integers. Now, how do you represent consecutive integers? Just consecutive integers. Like 7, 8, 9. They differ by how much? Right, the difference between a pair of consecutive integers is 1. So if I let x be the first integer, then x plus 1 is the next consecutive, and the one after that is x plus 2. If, however, I'm talking about even or odd integers, like 3, 5, and 7, what's the difference between two consecutive odds? 2. So I have to then use, in this case, x plus 2, and x plus 4. What happens if I have consecutive evens? Right, x plus 2 and x plus 4. Don't think that because I'm adding 2 on, it's making it even, because I'm starting out with an odd number. And when you take an odd number and you add on 2, you still keep an odd number. Okay? So let's see, the product of the ages. And which equation could be used to find Jeremy's age, J, if he is the younger one? So if Jeremy is the younger one, and that's represented by J, how are you going to represent Sam's age? Sam's the older one. Right, J plus 2, and then what you're going to do is to take J, it's a product, times J plus 2 is 783. So now which one of these looks like the one you want to use? What do you think about A? Any other thoughts? Let's take a look. All right, in this case we did J and J plus 2. You'll notice now that the product is J squared plus 2 times J. You have to use your distributive property. So this now gives me J squared plus 2J equals 783. So you have to remember the distributive property on that one. Okay, coin problem. This again is a Regents question. All right, now you have to remember there are two things to consider. First is the number of coins, and then the value of those coins. What's the value of a nickel? 5 cents or 0.05. Value of a dime? 10 cents or 0.10. Value of a quarter? 25 or 0.25. What's about the value of a dollar? 1.0. Okay? So those are all critical pieces. So in this case now, John has 4 more nickels than dimes in his pocket. Well, this tells me, in this case, that the number of nickels depends on the number of dimes. So I'm going to let x represent the number of dimes. How will I represent the number of nickels? He has 4 more nickels than dimes. Okay, I'm going to use x and then x plus 4. So I notice in this case now that I've got either A and B as my choices. This is a 4 times x, but if it says 4 more than, that means I have to add on the 4. And now what you notice is that x represents the number of dimes, but what's the value of the dimes? Well, it's not 0.05, it is 0.10. And just as a double check, here's the number of nickels, and that's the value of 0.05. So the answer would be choice B. Okay? And again, please make sure that when you do these problems, you write down your let statements up above. If x is the number of dimes, then, this is not another let statement, it's if x is the number of dimes, then it follows that x plus 4 is the number of nickels. And the value of the dimes, the value of the nickels. Okay? Okay, consecutive integer word problems. We talked a little bit about those before, and you have, in this case, consecutive integers are x plus 1, x plus 2, x plus 3. Consecutive evens and consecutive odds, x plus 2 plus 4 plus 6. Okay, so that would be a typical example where the sum of the second and the third is equal to the first. So we have the second one, third one is equal to the first one. Well, that doesn't make too much sense because usually they're getting larger and larger, but I notice in this case that when I solve I get -6. Be careful when you add on the 2. You get, in this case, -6 plus 2, which is -4. -6 plus 4 is -2. So these are your three integers, and those are all evens. Okay? Ratios. All right, a couple of ways you can work with ratios. The ratio of the length is 5:3. You could also write this as a fraction, 5 divided by 3. That would also be a ratio. So in this case, if you were told that the length of a rectangle and the width were in the ratio of 5:3, if you use the relationship 3x and 5x, that will also be 5x is to 3x as 5 is to 3. That simplifies. And then to find the perimeter, you're going to take twice what they call the semi-perimeter, which is the length and the width, and you're going to double that. So we find in this case that when solving, the x value is 3. Okay, here's another one using ratios. This is a Regents question. Take a look at it. Takes a minute to figure out all the things. Peyton is a sprinter who can run the 40-yard dash in 4.5 seconds. He converts his speed into miles per hour, as shown below. Which ratio is incorrectly written to convert his speed? Anything stand out? Right, remember what we want to do is to have this done in terms of miles per hour. So we have hours over here, and we need to have, in this case, the units simplifying and dividing out. So the yards in here will divide out. The seconds here will divide out. But what's the problem with this unit in here? Right, we really want minutes over feet. All right, the third ratio should be the reciprocal so that the correct units of measurement are left after simplifying. Let's just go back a minute and take a look. All right, so if you put the minutes up here and the feet down here, you'll notice that the yards divide out, the feet will then divide out if that's in the denominator. The seconds divide out, and this now had been moved up into the numerator, and that will simplify as well. Okay, so that's the one you have to change. Okay, percents and application. Percents are always based on 100, and if you have 100%, how would you write that as a decimal? 100%. What's 50% as a decimal? 0.5. What about 25%? 0.25. So what you're doing then is moving the decimal point over 2 places to the left. If you have 100%, when you move that over 2 places, you get the number 1. Okay? One whole quantity. All right? And if you wanted to, in this case now, start out with a particular problem here. In an election, 13% of the total votes polled is announced as invalid. 62% of the total valid votes has been polled in favor of the winning candidate. Find the number of votes received by the winning candidate if the total number of votes polled is 120. Well, we've got two different ideas here. It says 62% of the total valid votes, and it said over here that 13% of the total votes are invalid. What percent are valid?
62.
I want 62% of the valid votes were polled in favor of the candidate. But if 13% are invalid, then the difference of 87% are invalid. So the first thing we need to do is to find out a couple of ways of doing this. Again, the 13% are invalid. So we'll find out the total number of invalid votes. So I want 13%, which is 13 over 100, times the total number of votes, which is 15,600, To find the number of valid votes, I could simply subtract that to get 104,400. Another way of doing it, which involves only one step, after you get the 87%, is to take 87% of the 120,000, again, getting you the 104,400. And then to get the number of valid votes for the winning candidate, I want 62% of the number of valid votes. And that's your answer. Okay, so you have to make sure that you're looking at the same pieces of information each time, not just the numbers. Okay, this is a Regents question. Radio station did a survey to determine what kind of music computations or probably compositions to play by taking a sample of middle school, high school, and college students. They were asked which of the 3 different types of music they preferred on the radio: hip-hop, alternative, or classic rock. The results are summarized in the table below. So we have it done by middle school, high school, and college, the number in each group for hip-hop, alternative, and classic rock. And it says, what % of college students prefer classic rock? So what do you need to do? What % of the college students? Do you need to add up all of the students?
Yes.
What do you think? Just the college students. What % of the college students? So if I add up the college students, I have a total of 50. Now here's another trick you might like. If you look at 16 and 20 and you add those to get 36, and then you have 14 over here to give you 50 altogether, I would probably have looked at this and said 16 plus 14 is what? 30. And then add the 20 on. I try and do it in groups of 10s or multiples of 10s. It makes it a little bit easier. So now I have 50 students, and how many of these college students prefer, in this case, classic rock?
14.
So 14 out of 50, but remember they want a percentage. So you can either take your calculator and divide 14 by 50, or you can do a ratio and convert it to 28%. Okay? So total number of college students, 14 college students prefer classic rock, and then take your fraction. Okay? Okay, here's another Regents question. Student invests $500 for 3 years in a savings account that earns 4% interest per year. Okay, no further deposits or withdrawals are made during this time. Which statement does not yield the correct balance in the account at the end of 3 years? Okay, so what does this mean? How do they figure out the interest? How do you figure out how much you have at the end of the first year? Does interest increase the amount that you have, or does it decrease? It increases. So which one of these can I eliminate? Right, because here I have 1 minus the interest rate.
Isn't it asking for which one is not?
Mm-hmm. Okay. What about all of these other ones? Well, let's take a look. This one is the one that you want, because in this case, when you have the subtraction, you're taking out of the account. You're not adding that interest amount in. And if you look over here, when you find the interest at the end of the first year, you're taking your $500 times 1.04, which is the original principal plus the interest. That gives you, in this case, the interest for the first year, using a distributive property over here. So you had 500 plus 500 times 0.04, so that's the original amount. This is the interest. Now, after you have that interest in the bank for the first year, the next year, the second year, you're going to get interest on the interest. Not just the $500 initially invested, but what's in that account right now. And that turns out to be, in this case, $540.80. That's what you're going to get added into the second year. The third year, remember now, you've got interest from the first year, you've got interest from the second year, and then you're going to find out 4% of that larger amount. And then you're going to add them all together. So actually, this is the same thing as 1.04 times 1.04 times 1.04, which is the same thing as getting the interest for the 3 years. Okay? So choices 1, 3, and 4 all indicate a growth rate because you're adding on the 4%. Choice 2 showed a loss. So again, if you read the question carefully and think about what they're simply asking you, many times you can figure out where it's going. right, variation. There are two kinds of variation, direct variation. And that's like if the temperature in the room gets increasing, what happens to the volume of your balloon if you bring a balloon into the room? How many of you ever bought a balloon in a store and you've taken it outside? What happens to it if the weather's really cold? It starts to shrivel up, doesn't it? And then when you bring it back inside again, if the temperature in the house is warmer, that balloon will expand. So if you are in a room with a balloon, if the temperature is increasing, the volume of the balloon will also increase. All right, and that's called direct variation. The other one is indirect variation. That reminds me of a seesaw. If one goes up, the other one's going to go down. And in this case, what you're noticing is that for the direct variation, if you take the b value and you multiply it by a constant, that's going to influence the a value in the same direction. That's called the constant of variation. In this case, for indirect variation, they're said to vary inversely, and in this case, we find out that if you take a times b, that's going to equal a constant k. So for example, you might think about taking 5 times 20 and taking 4 times 25. If you increase one, the other one has to decrease to maintain that balance. Okay, so here's one. You can set different ratios on this. For traveling a distance of 50 miles, John paid $30 to the taxi driver. Maybe it's Uber nowadays. Find the cost paid by John when he travels for a distance of 35 miles. How would you set that up? You want a ratio. If one increases, the other one's going to increase also. The longer he travels, the higher the cost. So what you could do is to say, in this case, that the ratio of 50 miles to $30 is going to be the same as the ratio of 35 miles to the cost. And then you're going to take the cross product, product of the means equals product of the extremes. 5a is 105, a is equal to 21, and that would be the cost paid on 21. On this one, you'll notice, in this case, that you have the distance to the number of miles and the cost, and again the distance and the number of miles. So you're setting up 50 is to 30 as 35 is to the cost, and again product of the means and the extremes, you're coming out with 21. Okay, mixture problems. These are really fun if you have a little gimmick, and what I like to do is to set up buckets or little pails, and this is another way of doing it as well. I'll show you one later on. But you're mixing bleached flour with $4 a pound and unbleached flour costing $3.25. He wants 80 pounds of the mixture, so that's the total. So we want to find out how much of each he has to put together to make that mixture. He's going to sell it at $3.80 per pound. So we have the quantity, the cost per pound, and then the total cost. The quantity of bleached flour we're going to say is X, and if I need 80 pounds altogether, then 80 minus X is going to represent the difference. That's what's left. The cost per pound was given to me, and now if I buy X pounds at $4 per pound, the total cost is 4 times X. If I buy 80 minus X pounds of unbleached flour at a cost of $3.25 per pound, again, the cost times the number of pounds. This all together, when I mix the bleached and the unbleached flour, has to give me an 80-pound mixture that I want to sell for $3.80. Use a distributive property, you're going to combine your like terms, and you're going to find that your X value is 58.6. So there's 58.6 pounds of bleached flour and the difference now of 21.4 pounds of unbleached. Okay? Here's a word problem. Why don't we try setting this one up? Last week a candle store received $355.60 for selling 20 candles. Small candles sell for $10.98 and large candles sell for $27.98. How many large candles did the store sell? All right, so why don't you take a minute and see if you can do this one. Okay, Emma, get the equation set up. How many people let X represent the number of large candles? All right, did anybody let X represent the number of small candles? Okay, here's what I would suggest. All right, Jacob, on this one, when you start out by looking for the number of large candles, let that be your X value, because this way when you solve the equation, you're already finished. You've got your X value, which is the number of large candles. If you let X represent the number of small candles, then when you get your answer, you're going to have to subtract it from 20, and you still have that last step. And the problem is that quite often people will think, oh, I've got the value of X, I'm done. So let that be your variable to start with, and you're not apt to run into a problem then. All right, so here again, the large candles is X, and you have the cost of the small candle times the number of those, the cost of, this is for the large candle, the cost of the small candle times the number of those candles, your total proceeds. And when you get all finished, you sold 8 large candles, which was choice B. Okay. If you come up with a fractional value, what do you think happened? Something went wrong, because the number of candles should be a whole number. All right, so just be careful. In other words, think about what kind of an answer you would expect. If you came up with a negative number, if you came up with an irrational number, if you came up with a fractional value, chances are something went wrong in your math. Go back and double check. Okay, fraction word problems. These have been around for a long time. You don't see them too often, but I just wanted to show you how to set something like this up. Numerator of a certain fraction is 8 less than the denominator. If the numerator and denominator are each decreased by 5, the resulting fraction equals 1/3. That does not mean that the numerator is 1 and the denominator is 3. It simply tells you that the fraction, if it is reduced to an equivalent fraction, might equal 1/3. So you could have 3/9, you could have 9/27, anything like that. They want to know the original fraction. So what would you let your X value stand for? What would be a good choice, numerator or denominator? Denominator, good. So if you had X for the denominator, how would you represent the numerator? It's 8 less, so it's going to be, X is your denominator. How would you represent a numerator that is 8 less? Go ahead. Anybody? The denominator is X and the numerator is 8 less, so it's going to be X minus 8. So they use D for denominator. That makes it a little bit easier also. You're going to then decrease the numerator and denominator by 5, and that resulting fraction is going to be equivalent to 1/3. Combining like terms, you have D minus 13 divided by D minus 5 equals 1/3. Take the product of the means equals product of the extremes. Solve the problem, you get 17. So let's just see how that works out. The denominator is 17 and the numerator is 9. Then it said if you decrease the numerator by 5, what does that become? 4. And decrease the denominator by 5, and that becomes 12. So you'll have 4 over 12, which is the original 1/3. And again, take your answer and check when you get finished with the problem to make sure it works. Okay? Another one, separate 50 into 2 parts, such that twice the larger part is 10 more than 3 times the smaller part. I don't know which is a smaller, I don't know which is a larger. It doesn't make any difference, because you're still going to be able to solve the problem, and some of you will come out with the larger one as your solution, some of you will come out with the smaller one as a solution. All right? So this now becomes the smaller as X. 50 minus X is the difference, which is the larger part, and we have twice the larger part is 10 more than 3 times the smaller. All right, and when you see that word is, you know that that's going to be your equals. Okay, you're welcome. So now distributing, we have 100 minus 2x equals 3x plus 10. Solving, x is 18, so the smaller part is 18, the larger is 32. If you had let x represent the larger part, you would have ended up with 32 as your value for x. And then when you'd subtract, you would end up again with the other piece. Okay? Percent mixture problems. let me just talk you through this one. In this case, you've got a lemonade that contains 3 ounces of lemon juice, that's a quantity, and 12 ounces of water. So that's the original lemonade. How much pure lemon juice must be added to produce a solution which is 25% lemonade? If the original lemonade contains 3 ounces and 12 ounces, what's the total? How much lemonade altogether? 15 ounces. And it says in this case that 3 of the 15 ounces, or 1/5, is lemonade, is lemon juice. And that's what percentage? 1/5. 1/5 is what percent? Trusty calculators, right? 20%, right? So now they want to increase the strength of that lemonade to 25%. You're adding pure lemon juice. So I like to do it in terms of little buckets, and I think it makes it very clear to see what you're doing and also how to set up the equation. So I have the lemonade that I'm starting with, I have the pure lemon juice, and here's my final lemonade. The first piece is 15 ounces altogether. You just told me it was 20% lemon juice. Now I have pure lemon juice, which is 100%. And here's that 100%, which I'm going to translate into that 1.00. The final solution is 25% lemonade and 15 plus X ounces. Again, you're going to take the lemonade, add in the lemon juice, and that's going to give you the final lemonade. So it almost shows me, just by setting up the 2 little buckets, exactly what the equation is going to be. And then when I solve, just as I would normally do, I find out that 1 ounce of the pure lemon juice must be added. Okay? Here's another one. Chemist is making an iodine solution. He needs 120 milliliters containing 39% iodine, but combining a solution of 30% iodine with a solution containing 42% iodine. You want to make sure that the 39% that they require is between the 2 things that you're mixing. How many milliliters of each solution will be needed? So if I now look, again, I'm setting up like little buckets, or in this case test tubes. I have X milliliters of the 30%. I need a total of 120, which means that 120 minus X represents the number of milliliters at the 42%. So it's the value for this liter, the value for this amount equals the amount over here. And again, you just run it straight through with your distributive property, combine your like terms, and it needs 30 milliliters. Okay? Okay, we're going to stop here for a few minutes, okay? And then we're going to take a look at monomials, polynomials, exponents, and factoring. Okay, so first of all, we know that with monomials, those are single one terms. And again, we talked about like terms before. A lot of the things that we've talked about, like distributive property, multiplying 2x times 3x, you get 6x squared. We talked about some of the ideas with monomials and multiplication, but we're trying to just separate things a little bit so you can get the rules down. Okay, so first of all, like terms in this case have to have the same base and the same corresponding exponents. So for example, if you have an AB squared and an AB squared, those are like terms because the bases are AB and the squaring is on the B for each one of these. If you had had, let's say, a 12A squared B, that would not be like terms to these because the exponents are not on the same corresponding bases. So you have to be careful with that. Okay, multiplication of monomials. Now we have some of the rules that we're going to look at. If you have the sum, if you're multiplying two monomials, you're going to take the product of the m to the x and x to the m and x to the n, and you're going to add the exponents. And if you think about the fact that if you had x to the third times x to the second, you'd write x out 3 times for x to the third. You'd write x out x times x for x squared. You'd have 5 of them all together, which you could then rewrite as x to the 5th. So if you get stuck and you can't remember if you need to add or multiply the exponents, write out an example, and that will make things a little bit easier. All right, so in this case, x to the 5th times x to the 3rd, keep the same base, add the exponents, which becomes x to the 8th. Now, this is a tricky one because a lot of people tend to look at these bases and say, oh, well, I know -2 times -2 is 4. However, you'll notice that this falls into the rule of multiplying, in this case, like bases. So we're going to keep the exact same base of -2, and then you're going to add the 8 plus the 2 to get 10. Now, another thing you might want to realize is that if you have a negative number raised to an even power, it's always going to have what sign? It's always going to be positive. Because if you take a negative times a negative, times a negative times a negative, you do it 4 times, it becomes positive. If you have a negative base raised to an odd power, the sign will always be negative. So there's a little shortcut that you might try along the way. So here's one. We have -7a squared b multiplied by 4a squared b. And here's where I talked about writing things out a little bit. We have -7a squared b. We wrote it out in terms of its factors. We're now going to group the coefficients together, group the terms with like bases, the a's together, the b's together, and then we're going to follow the rule that we have for multiplying monomials. 2 plus 2 gives me a to the 4th, and this becomes b to the 2nd. If you have no exponent appearing on the b, the exponent is assumed to be 1. Okay? Power of a power. And again, you can always write things out with an expansion. If you have a power raised to a power, you're going to take the same base and you're going to multiply the exponents, m times n. So if you had x to the 5th raised to the 3rd power, that becomes x to the 15th. And again, if you run into a problem and you don't remember that, if you have x to the 5th cubed or raised to the 3rd power, it's x to the 5th times x to the 5th times x to the 5th. You have 5 x's, multiplying 5 x's, multiplying another 5 x's, so there are 15 of them all together, and that gives you x to the 5th. And here again, you'll notice I have a constant base. You're going to take the 6, which stays the same. 2 times 8 gives you 6 to the 16th. Right? If you have a quantity in parentheses, one term monomial raised to the m power, that m is going to affect everything inside the parentheses. So let's take an example. Here I have -5 x squared y to the 2nd times xy squared to the 3rd. Now, as I said before, you have -5, but you're squaring it, so what will the sign automatically become? Positive. So it's positive. I have x squared to the 2nd, this becomes x to the 4th. You're multiplying y to the 1st, so 1 times 2 gives me y squared. And here I have the whole quantity raised to the 3rd power, so it's x to the 3rd, and then y squared to the 3rd power is y to the 6th. Now I'm back to the same old rules of multiplication. Keep the 25. I have x to the 4th times x cubed, which is x to the 7th. Y squared times y to the 6th is y to the 8th. Okay, division of monomials. Now here again, this gets into some interesting situations. Let's look first of all at the fact that I have x to the m divided by x to the n. The bases must be the same. Here I'm going to consider m being greater than n. And what I'm going to do is the inverse operation. Think about when I multiplied, what did I do with the exponents? When I multiplied, I added. So if I'm talking about the inverse operation, when I divide, I'm going to subtract the exponents. So it's going to be m minus n. In the situation where I have the exponents are equal, where m and n are the same, well, this is really cool because what's x to the m divided by x to the m? Anything divided by itself is always 1. But if I look at the rule for the exponents in division, I have x to the m minus m, which becomes x to the 0. And you know anything to the 0 power equals 1. Again, you must stipulate that x can't be 0. You can't have a 0 base. And on this one, we're going to say that n is larger. You have more x's sitting down in that denominator. So this time, yes, if you had x to the m minus n, but that gives you a negative exponent, which means throw it in the denominator. So it's just more efficient to do x to the n minus m. Leave it in the denominator. Okay? Let's take a look. Here you have like bases again. Keep the negative 3. You have 6 of these up here. You have 4 of them down here. When I divide them out, subtract the exponents, I have negative 3 to the second power. And again, negative 3 times negative 3 is positive 9. Same thing happens over here. Take 10 divided by negative 5, gives me negative 2. A to the third divided by a. Numerator has a larger exponent, so it's 3 minus 1, leaving me with a to the second. B to the fifth divided by b squared. Again, the 5 is larger, so it becomes b to the third. Okay? And similar to the multiplication, if I have a fraction x over y raised to the m power, that exponent will affect both the numerator and the denominator. Okay. Okay, now negative exponents. I always wondered why it was negative. So somebody explained to me that if you took, let's say, 10 squared, what was that equal to? Right. If I divide that by 10, I get 10. 10 to the first is 10. If I divide 10 to the first by 10, I get 1, which is 10 to the 0. And again, anything to the 0 power is 1. And then if I take 1 and I divide it by 10, that's 1/10, or 10 to the negative first. So the rule is that if I have a negative exponent, it becomes 1 divided by a, and there should be an n in here also, by the way, 1 over a to the n. Let's look at this example. A to the 0, in this case, is 1. I keep the 4 coefficient. B to the second stays the same. C to the 0 is 1, and it simplifies into 4b squared. Okay, this one, again, you can separate it into dividing your like terms, or you can just simply work with it in this form. I have 20 divided by negative 4 is negative 5. Now, here I notice that the larger exponent is in the denominator. So yes, I could take a to the 2 minus 5 and get 2 to the negative third. If I have a negative, that goes into the denominator. Or I could use the previous rule where it says if the larger exponent is down here, leave it here and take 5 minus 2 to get the 3. Be the same thing. Over here, b to the 7th divided by b to the 9th. How many b's do I have as factors in the numerator? 7. How many b's do I have as factors in the denominator? 9. I have 2 more in the denominator, so I'm going to leave the b squared over here. Okay? All right. Now, fractional exponents. Whoop. Let's go back. Okay, fractional exponents. If I have an m divided by n, the n represents the root. So this, for example, would be the index on the radical. M represents the power. So I could write it either as, in this case, the nth root of x raised to the m power, or the nth root of x to the m, whichever makes it easier. And I would strongly recommend that you go to make things smaller. So sometimes taking the root is a smarter way to go, using this idea rather than taking x and raising it to the power and then dealing with something larger. So for example, over here, I have 4 to the 3/2. 2 represents the index. That's a fractional exponent, which means I'm going to take a square root. The 3 represents the power I'm raising it to. So in this case, what's the square root of 4?
2.
And then 2 cubed is 8. The other way I could have done it would have been to take 4 to the 3rd power and then take a square root. What's 4 to the 3rd power? 64. And then what's the square root of 64? 8. You're going to get the same answer, but why not work with a smaller number? It makes it easier. You can do that in your head. Here you have a cube root, which means that the exponent is 1/3. So I'm going to put this in parentheses, raise it to the 1/3 power, and remember now that each one of these individual factors is raised to the 1/3 power. So what is this 27 to the 1/3 really asking me to find? It's a cube root of 27. What number when multiplied by itself 3 times gives you 27? 9 times 9 times 9 is going to be huge. 3 times 3 is 9, times 3 is 27. It's going to be pretty small, okay? Because it has to be multiplied by itself 3 times. So it's 3. X to the first power, 3 divided by 3. What I'm doing is taking that 1/3 times each of these exponents. 1/3 of 6 is 2, and 1/3 of 9 is 3. Okay? So here is a Regents question. Let's see if you can figure out what it's going to be if you write it in a different format. I'll give you a minute to try this. All right, one thing you want to make sure of, B is, in this case, is a positive number. D is a positive integer. Any thoughts? If you look at A and C, where does the expression end up? In the denominator. And for that to happen, what kind of an exponent would you have to have? Negative. You don't have a negative. It said already that D is a positive integer. So you can rule out A and C. So now you have B and you have D. Well, let's go back to the original expression. You know that 3B is going to be your radicand, so that checks out in both. What does the D represent? That is, it's the root that you're trying to find. And then what does the 2 represent? You're raising it to the 2nd power. So if you look at B, this has a square root. The index is 2. Has nothing to do with D. If you look down here, you have a radicand, which is 3B, that checks. D is the index, which means I'm taking 1 over D, or the root, the Dth root, so to speak. And then you're raising the whole thing to the 2nd power. So it has to be choice D. Okay, again, try and eliminate your choices. All right, here's another one. This one has a negative in the numerator. So what is that going to tell you right away you probably want to do? If you have a negative in the exponent, you're going to take the reciprocal of this eventually. All right, so if you have m squared divided by m to the 1/3, what are you going to do inside the parentheses first? Let's subtract the exponents. If I take 2 minus 1/3, that's the same thing as 6/3 minus 1/3 is m to the 5/3 power. So m to the 5/3 power. And then I want to take that to the negative 1/2. Let's go to the slide that's following, because it will show you exactly what we're doing. We took m to the 5/3. So now you have a power raised to a power. What is that telling you to do with the exponents? Right. So if I take 5/3 times negative 1/2, I get m to the negative 5/6 power. And here again, you'll notice there's a negative, and I told you before, that goes down in the denominator. Whenever you see a negative, put it in the opposite position. And then this represents the root, the 6th root, and the power. So it's the 6th root of m to the 5th. That's your correct answer. Okay, again, we were able to eliminate 2 of them because I knew it had to end up with a negative. Okay, scientific notation. You see this in chemistry and some of your other biology courses. In this case, for scientific notation, you're going to express any very, very large or very, very small number in terms of a number between 1 and 10, 1 included, 10 not being included, and then you're going to multiply it by a power of 10. So 10 to the 5th represents 100,000. 10 to the negative 5th is going to take 1 and it's going to move it over 5 places to the left Very, very small. You can also think about 10 to the negative fifth as 1 divided by 10 to the fifth and do it that way as well. So if you have, in this case, 1,543,000 miles, you're going to find the first significant digit, which is 1, first significant non-zero digit. You're going to put a 1 over here, and then you have to figure out which way you want to move that pointer to get it to the original number. So I have to move it over 1, 2, 3, 4, 5, 6 places to the right. So it's going to be 1.543 times 10 to the 6th. Over here, what's your first non-zero significant digit? 2. Put your decimal point after the first significant digit, which is 2. And then to get to the original number, you have to move it over 1, 2, 3, 4, 5, 6, 7, 8 places, but you're going to the left, so it becomes 8 to the 10 to the negative 8. You're making it smaller. Okay? You ever seen Avogadro's number? Okay? You'll see about that in chemistry. Okay? Solving equations with rational exponents. Again, various different techniques on these depending upon the original problem. And here you'll notice that if you have x to the m divided by n and you raise it to the n divided by m, when you multiply those exponents, what happens? Right, the m's divide out, the n's divide out, you're left with x to the first, which is simply x. So on all of these types of problems where you have a rational exponent, you've got to somehow get rid of that. It's not only a power, but it's also that square root sitting down in there. So I'm going to use that little gimmick that we looked at up here. If I have 3/2 as my exponent, I'm going to use the reciprocal and multiply everything or raise everything to the 2/3 power. So now if I do that, 3/2 times 2/3 becomes, what's 3/2 times 2/3? 1, right? Same thing that we did up here. The 3's will divide out, the 2's divide out, so I have 2x plus 3. Now, 8 to the 2/3. Well, this is what we have to figure out. This 3 tells me I want a cube root. So what number, when multiplied by itself 3 times, gives you 8? 2. Get the smaller one first. And then 2 to the second power is 4, okay? The other way of doing this would be, say, 8 squared is 64, and then a cube root of 64. Again, you're going from the larger to the smaller. Keep it clean. So you have 2x equals 1, you had subtracted 3, x equals 1/2. Okay? Now here's one where there are exponents on both sides. Fortunately, the denominator is the same. So if you raise each of these to the 5th power, what you have is x squared minus 6x by itself, and then here you have, this should be 4 to the 2nd, which is 16. This should be an exponent over here. So we have x squared minus 6x. You're going to bring the 16 to the left-hand side, and then this is actually one that has to be factored. You're going to end up with x equals 8 and x equals negative 2. And we'll spend more time with the factoring, but I'm sure you've all familiar with that at this point? Okay, you've all been taught that. Okay, addition and subtraction of polynomials. In this case, a polynomial is many terms. A binomial has 2, think about a bicycle. A trinomial has 3, think about a tripod. And there are other types of names for, hold on here. Is that what we want? Okay. So in this case, when you're doing polynomials, you want to make sure that you have the like terms together. So if I look at 5a squared, which is the like term that I will combine it with over here? Which is the like term with 5a squared? Good. So I have 5a squared is 4a squared, and then I have plus a minus a becomes 0, and the plus 4. And then the other thing that they had done here was to factor out the 4. Not necessary, but another way of solving it. Now here's one where you have to be careful. It says subtract this from this. So it's going to be this trinomial minus this one. And if you get stuck, think about saying subtract 10 from 20. How do you do it? Subtract 10 from 20. You take 20 minus 10. So for this one, it's going to be this trinomial minus this trinomial. And what you have to remember is that every single term has to be subtracted. So make sure when you do this, if you set it up in a vertical fashion, that you put the minus and then the parentheses. So So 5x cubed y minus 2 of them gives me 3. 9x squared minus 4x squared is 5x squared. 4z minus a negative 5z now trips it to 4z plus 5z, which is 9z. Please remember that negative sign in front of everything. Okay, here is a Regents question. All right, now they're not going to make it simply subtract this from this. They're going to put some more words and descriptions in. So you have a company produces X units of a product each month. C represents the total cost for making them. R represents the total revenue for selling them. The functions are modeled by the cost equals 300x plus 250 and R of x equals negative 0.5x squared plus 800x minus 100. The profit, how much they make each month, is the difference between how much they take in, their revenue, their sales, and how much it costs them to make it. So what this is really saying to you is that you want to take R of x, which is a trinomial, and subtract the binomial C of x. Okay, so I have in this case the profit. So I have no x squared terms here, so I'm going to keep negative 0.5 x squared. Well, that checks out for all of them, can't eliminate anything. And here's where the catch comes in. I now have to subtract this term. So I have 800x minus 300x is 500x. Well, that works over here, but they're trying to make sure that you're paying attention because you have to subtract the 250. And if I have negative 100 minus 250, what does that become? Negative 350, right? So it's going to be choice B. Okay? All of these are there to try and throw you off a little bit. Okay? So there's your choice. Choice B. Okay? Multiplication of two binomials. How many people have heard of foiling? Okay? And that represents the first times the first, the outer product, the inner product, and the last times the last. Some people use a box method. They set up a little box that's 2 by 2. Have you ever done it that way? And they multiply the area for those boxes and then they add them together. Most people, I think, are probably comfortable with the FOIL method. And you'll notice in this case, if you want to find the product, it's basically a double distributive property. You're taking the negative 5x times this binomial, the positive 6 times this binomial. But to keep track of the pieces, if you do the first times the first, that's 15x squared. The outer product is positive 20x, a negative times a negative. The inner product is negative 3x times 6, which is minus 18x. And last times the last is negative 24. And then most often you'll find that the inner and the outer terms can be combined. And that now simplifies to 15x squared plus 2x minus 24. Okay, multiplication of two polynomials, basically the same thing. You are using a distributive property. So if you have, think about it, 2 terms multiplying 3 terms, how many terms should you have in the product? 2 terms times 3 terms you should have? 2 times 3 is 6. You should have 6 terms. So you're going to take the 5x and you're going to multiply each of the 3 terms in the trinomial. You're going to take the minus 7 and multiply that by each of the 3 terms in the trinomial. Use your distributive property, and then you're going to group your like terms. The 10x cubed is sort of off by itself. You have a 30x squared and a negative 14x squared. They combine to give you 16x squared. Negative 20x squared and a minus 42x gives you a negative 62x, and then you have, in this case, the 28 over here. Now, if I have a lot of terms I'm trying to combine, some of you, when you get down to this point and you start combining your terms, will tend to cross them out. Then if you want to go back and double check, you can't see what you've written. So what I like to do is maybe underline the like terms. So 10x cubed is sort of off by itself. Just put a single line underneath that. Then I might look in descending order, which is the x squared term, put a circle around that, put a circle around the other x squared term. You then can account for all the terms. The negative 20x, I might decide to put a little triangle around that and a negative 42x with a triangle. So those are like terms, combine those. And then the 28 is just sort of the tag along at the end. But you know that you've accounted for all the terms. Frequently people will go through and combine terms and all of a sudden leave something out. If you cross them out, then you're not going to be able to see them clearly. So what I would suggest is just put a little mark or a dot over them to make sure you've used it. Okay? Here's one. What I'd like you to do is to try this one. The nice thing about this is that you've got a FOIL method in here. This is really the same thing as 2x minus 3 times the quantity 2x minus 3. This is not 2x squared minus 3 squared. It's, write it out as 2x minus 3 times 2x minus 3. Why don't you give that one a try, and then you're going to subtract that trinomial from 5x squared, and watch those signs with the negative. All right, check your results when you get finished. Okay, how'd we do? Good news? Okay, so again, the trick here is if you have 2x minus 3 times 2x minus 3, that's the trinomial 4x squared minus 12x plus 9. You've already combined your inner and outer terms. That trinomial is being subtracted from 5x squared, which means you have to subtract each and every term. So I just go through removing the parentheses and reversing all the signs. So the positive, negative, positive became minus, positive, minus, and then combine your like terms. Okay, division of a polynomial by a monomial. We did some monomial division before, but the only thing that I want to point out here is that what you're doing is taking each one of these three terms and dividing by x squared, y squared. You have to divide it into each one. And just to make sure that you don't do it just piecewise with just, let's say, the first term in the trinomial in the denominator, write each one of them out separately and simplify as you go through. It's probably safer. Okay, division of a polynomial by polynomial, this is known as your long division. And in this case, you've got your dividend, you've got your divisor, and the result is your quotient. Have you gone through this, or have you done synthetic division at all? You done synthetic division? Okay, we won't do that then. Okay, but let's say I wanted to divide 52 into, let's say, 839. When you start with a problem like that, do you take 52 or do you say, well, let me try 50? It's easier for me to think about 50, right? As an approximation. I don't do 52 right away. I say, let's work with 50. But then when I get that quotient, I take what I found in the quotient and I multiply it by the entire 52. So this is sort of the same strategy. I'm dividing the whole thing by x plus 1. But just to get started, I'm going to consider x squared divided by just the x. Leave the 1 off to the side right now. And what's x squared divided by x? Gives me x. So now I've got the x, and like I did with that 52, I'm going to take x and multiply it by the entire x plus 1, which gives me x squared plus 1x. Line it up under the like terms. And then you're going to subtract that product. So x squared minus x squared is 0, and that's great because I had divided it out. 4x minus x gives me 3x. And now I'm going to start the second division. You can bring down the 3 if you like. Take the 3x, again approximate x divided into 3x 3 times. Now take that 3 and multiply by the entire x plus 1. I get 3x plus 3. Parentheses, subtract. Do not forget the parentheses and the subtraction. So 3x minus 3x is 0, 3 minus 3 is 0, and that's the remainder. Well, what that also tells me, if the remainder is 0, is that x plus 1 is a factor. And we'll talk about that in a few minutes. So here's a division problem. You'll notice in this case that when I start out with 2x into 4x cubed, I have 2x squared, so I have to actually do a little bit more in the problem. All right, let me go through this with you with a division. All right, so on this one now, 4x cubed divided by 2x, that's that approximation again. I start with that first term. I get 2x squared, take the 2x squared and multiply it by the entire binomial, and that gives me 4x cubed plus 6x squared. Parentheses, subtract. And I'll say that over and over again. 4x cubed minus 4x cubed is 0. 0 minus 6x squared is negative 6x squared. Bring down the 5x. Now I'm going to take the negative 6x squared, divide by 2x, and that goes in negative 3x times. Take the negative 3x, multiply the entire binomial for negative 6x squared minus 9x, parentheses, subtract. These will, negative 6 plus 6x squared becomes 0. 5x plus 9x is 14x. 2x divided into 14x goes 7 times. Again, multiply by 7. I get 14x plus 21. Put it down here. Parentheses, subtract. 14x is subtract out. 10 minus 21 is negative 11. That's the remainder. Now the problem here had asked you to write it as, in this case, a trinomial with the remainder. You know that your denominator is always going to be what you're dividing by. So the 2x plus 3 will have to be in that position. And now what you're noticing is that your quotient is 2x squared minus 3x plus 7 plus the remainder divided by 2x plus 3. This is a Regents question. Okay? Now, what happens if you can't remember how to divide? Well, here's a gimmick. You know that if you were to take this value over here and multiply your trinomial, you're going to get another trinomial. If you then subtract 11, you should get the term that you started with, that expression. The other thing I want to mention is that when I looked at the original problem, you'll notice that there's no x squared term. And when I start the actual problem, you'll notice that I have an x cubed. I put in a 0x squared. That's my placeholder. Then I have the x to the first and then the constant. It's written in standard form. And that's because when I start doing that multiplication through by the 2x squared and then 3, I pick up a 6x squared. And if I didn't have that 0x squared in as my placeholder, things would not align easily. So you're doing it to save yourself all that alignment. Okay, synthetic division you haven't done, so we're going to skip that. Solving fractional equations. This is one where you have the variables in the denominator. And the idea is, I don't like fractions, and chances are a lot of people don't like fractions either. So my goal is to get rid of the denominators. And what I'm going to do, this is only if you have an equation, is to multiply through by the least common denominator, the LCD. So let's look at the denominators. I have an x minus 5, that's one factor. I have an x, that's another factor. And fortunately, I have an x and an x minus 5 over here as well. So my least common denominator is x and x minus 5. The one thing you want to keep in mind is that if you have variables in the denominator, what can a denominator ever equal? It can never equal 0. So x cannot be equal to 0. I've got that stated. And what value of x would make this equal 0? Right. I can't have x equaling 5 either. So I have to exclude those two values. So now, let's go back to the original problem, multiply through by the LCD. Some people like to just write it out in front with brackets, like we did over here, or some people write the LCD next to each one of the terms, because then you'll notice that in this case, and this is just to show you what goes on, the x minus 5 factor will divide out, leaving me with just the 6x. Here the x's will divide out, leaving me with the x minus 5. Distributive property, combine like terms, and solve for x. Okay, so there are a lot of little gimmicks on this, things to work about. And then you want to make sure that when you get all finished, your value over here that you come up with is not one that you have excluded. Otherwise you would have no solution. All right, and make sure that you double check. Okay, greatest common factor. We're going to now start getting into factoring. The greatest common factor, the GCF, is always the first thing you want to look for. Okay, so in this case, if you look at this particular trinomial, you have 10, 20, and 2, and LCD, or the GCF for those three values would be 2. Here you have 4 A's, you have 2 A's, you have 1 A, so you need 1 A. That's what they have in common. And then they have a B squared, a b to the first, and a b squared. The most that they would share would be 1b. So we'll take out, in this case, the 2a. Why does this have a b squared? Oh, this one should have a b squared written on it. I'm sorry. Okay. So assuming that it has the b squared written on it, the b squared is what they have in common. And when I factor that out, I'll need to have a 5a cubed remaining, a 10ac remaining, and a plus 1. So that's a placeholder. Remember, as your double check, if you have a monomial times a trinomial, you're going to get your 3 terms. If you had left out that 1, you'd have a monomial times a binomial. You'd only get 2 terms. So you need that as your placeholder. Okay, difference of 2 perfect squares. Those are always written in the form of a squared minus b squared. Let me give you a couple of examples. 121 minus a squared b squared. 121 factors, perfect squares are 11. Those go in the first places. The square root of a squared b squared is ab. You'll have the sum and the difference of the square roots. Okay, that's fairly common types of factoring. When you multiply these together using the FOIL method, what happened with that outer and inner term? Outer term was negative 11ab. The inner term is a positive 11ab. What happens when you add them together? Right. They add to 0, so you're missing that middle term, and that's how it's easiest to factor. Now this is one that's a little bit different. What I did over here was I had x plus 7 squared minus 5 minus x quantity squared. This actually is the first term, like your a. This is your second term, like your b. So I'm going to factor it into the sum and the difference of the square roots. So x plus 7 is going to go in the first position in each bracket. 5 minus x is going to go into the second position in each bracket. And then I'm going to clean it up. So I have 5 minus x plus the x plus 7. The x's will subtract out, and I'm left with 7 plus 5, which is 12. And here the x minus a negative x becomes 2x, and 7 minus 5 is 2. So this difference of 2 perfect squares actually simplified into this. And you could actually go one step further and make it 24 times x plus 1. Okay? Remember, the sum of 2 perfect squares cannot be factored. All right? And if you think you're going to factor it, use your FOIL method and double check. Then you know you're going to be okay. Okay, trinomials. This gets to be a little bit tricky. What you have to notice in this case is that if you have a lead coefficient of 1, and you'll notice that everything is written in descending order, x squared, x, and your constant. In this case, what you want to do here is to think about 2 numbers that multiply to negative 36 and add up to 9. So can you think what might work? 2 numbers whose product is negative 36 add up to 9. Well, you've got a couple of possibilities. You've got here for the 36, you've got 9 and 4, you've got 2 and 18, you've got 12 and 3. Is there any of those combinations that somehow give you a difference of 9? Right. So let's put in the 12 and the 3. And what you'll notice now is that if you make the 12 positive and the 3 negative, when you add the outer and the inner terms together, you're going to get the positive 9. If you had reversed the signs, then this would have been negative. Switch them back. Okay? Now, suppose the lead coefficient is not 1 as it had been here, but it happens to be 2. Well, you know in this case that 2 is a prime number. What's the only way of factoring 2? 1. Right. So we'll start out with a 2x and a 1x. All right, and then I need a 15. Well, fortunately, 15 has only factors of 1 and 15 and 3 and 5. So now the question is, where do I put the 3 and the 5? Okay? So you're going to either 3 and 5 or the 15 and the 1. And you can play around with some of the combinations in this case. If you put in, you need to get negative 7x. So if I put in the 2 times the 5, that gives me 10. This gives me a 3x, and I need to get a negative 7, which means that the larger product must be negative. So I'll make the negative 5 times the 2 for negative 10. This becomes a positive 3. Okay? Okay, grouping. Generally, you're going to use grouping if you have more than 3 terms. This one happens to have 6, and sometimes you can group it 3 and 3. Sometimes you can group it 2 and 2 and 2. So let me show you this example. You might try saying, well, in this case, you've got an a cubed, you've got an a squared, you've got b terms. How do I arrange those? Well, let's try putting it in a little bit of order. So I'm going to take the a cubed and the a squared. I also have an 8 and a 4. What do they have in common? A 4 and an a squared. So what I have left then, when I factor out the 4a squared, is the 2a. And here's that placeholder, 4a squared times what gives me negative 4a squared? I need the negative 1. I'm also going to put together the negative 6ab and the 3b. They have a b in common. So I have these two grouped together. I have a negative 3 and the b that they share. What I'm left with is 2a minus 1. And I'm getting very excited now because I noticed that 2a minus 1 appeared in my first term as well. And then if I look at the remaining pieces, sure enough, there's that 2a minus 2a plus 1. It's close, but in this case, it has the opposite sign. So what I will do is to factor out the negative 1 and make a 2a minus 1. And now what you'll notice is that you have, again, 3 terms. Each of them have 2a minus 1 in common. Factoring that out in front, I'm left with 4a squared minus 3b minus 1. Right? And you can always check by multiplying, doing the double check on that. Okay, sum and difference of two perfect cubes. This is one that you really kind of have to memorize, and I apologize. Some of your perfect cubes are 1, 8, 27, 64. They're probably not going to go up too much farther than that, or maybe 125 for 5 cubed. And what you'll notice is that it's a cubed plus b cubed. Well, the first obvious factor is going to be a plus b. And here's where the gimmick comes in. Have you ever heard the trick SOAP? Okay, so here's what happens. The first binomial will have the same sign. That's your S, same sign. Then it's, in this case, the same again. So it's going to be positive a squared, opposite, so it's going to be, if this is positive, this is minus the product ab, and then always positive is plus b squared. So if I look at this one, it's going to be a plus b. I'm going to keep a squared minus the product plus b squared. A cubed minus b cubed, I'm going to take a minus b. Keep the same sign. This is going to be a squared, always starting out the same way. This is going to be the opposite sign, so it's plus ab, always positive. Now what you have to remember is that if you want to factor something like 4x cubed minus 256, it begins to look like a perfect cube, but there's something that's not quite into that form yet. So I'm going to factor out a 4, a GCF of 4, leaving me with x cubed minus 64. Well, I think 64 is a perfect cube. I'm going to rewrite that as 4 to the 3rd power. So now I have the 4. I have the difference of two perfect cubes. One factor will obviously be the x, the minus, and the 4. Then I'm going to take the first term and square it. I'm going to take the opposite sign for the product, which is 4x, and then the last term squared, and that's always positive for plus 16. Okay? Get the hang of this? Okay? So in this case, SOAP, keep the same sign for the first factor. This one's always going to be positive. Take the opposite sign, and then the last one's always positive again. Okay, factoring completely. This means that as you go through a problem, you look for your GCF, you look for the difference of two perfect squares, you look for the trinomial, you look for grouping, and then you look for the sum and the difference of two perfect cubes. So that's the sequence that I usually go through on these problems. All right, so here's an example. This is a Regents question. All right, this is the first time I've thrown an x to the 4th at you. However, how could you rewrite that? X squared times x squared. So what I'd like you to now do is to see which one you can factor that into. If you run into a problem, what you can always do is FOIL these binomials. All right? So this is the difference of two perfect squares. What I've done is I've written x to the 4th as x squared times x squared, square root of 16, making it positive 4 and negative 4. And you can further factor that because this, again, is the difference of two perfect squares. The Regents exam actually leaves it in this form, although if you had continued, the x squared minus 4 could be written as x minus 2 times x plus 2. Okay, factored completely. What do you notice about each of these terms? What do they have in common? Right, so we're going to take out a GCF of x, which we have over here. Let me go to the next step. So now, This is when you take out the x. This is what you have left. So now you're going to set up, don't leave that x out again. You have an x squared, 2 sets of parentheses, x times x. I need 2 numbers that multiply to -30 and add up to -13. The larger product has to be negative. So I'll take a -2, which gives me a -15x, a 2x, so that nets out to a -13. So that's choice C. Okay? Factoring completely. And again, on this one, which factoring is incorrect, what I would probably do on this one is to simply FOIL or go through the distributive properties. Here's the difference of 2 perfect cubes. All right, so there's where you might see that. A minus 2, remember 8 is the same thing as 2 cubed. So it's A minus 2B, and then you're going to have the first term A squared, the product of plus 2AB, and again notice that it's the opposite sign from SOAP, and then a positive 4b squared. You can do that again by multiplying out and checking, all right? And they went through all the different products as well. Okay, simplification of radical or rational expressions. Most of the time, again, it comes into factoring. Take your numerators and denominators, factoring completely, divide out your common factor. Okay, solving equations by factoring. You've all done quadratics, I'm assuming. Okay, so on this one, for example, you want to solve for A, you're going to set it equal to 0. You can't factor and solve an equation unless it's set equal to 0 to start with. That's critical. And in this case, factoring out the A, get the 2 binomial factors, and then if you have a product of factors equaling 0, what do you know about one of those factors? The only time you're going to get a product of 0 is if one of those factors equals 0. So we have A equals 0. This tells us that A could be 1/2 or A could equal -1. So I have 3 solutions. Okay? One trick on this one, you can solve the equations and get your values for x, or you could take 2/3, substitute it in and see if it checks. You could take -4, substitute it in and see if it negative checks. There's always a way of perhaps looking at it in a different way. The only disadvantage is that you'd have to go through several different substitutions. Or you can take it and factor, set each factor equal to 0, and solve that way. Okay? All right, perimeter and area problems. Do you want to, it's 7 o'clock already, do you want to do one problem application? Okay, let's wrap it up with that. So this actually is a Regents question. Joe has a rectangular patio that measures 10 feet by 12 feet. He wants to increase the area by 50% and plans to increase each dimension by the same amount. Which equation could be used to determine x? So now, first of all, it says he wants to increase the area by 50%. This is the original garden. What is its area currently? It's 10 by 12, so the area is, right. Now, what's 50% of 120? 60. So he wants to make it a total of 180, right? It's 120 to start with. He wants to increase it by 50% or half of that. So he wants to increase it by 60, bringing the 120 plus 60 up to 180. So right away now, I notice that A is not appropriate. All right? A is not appropriate because it's got 120. So now, let's take a look at the problem. What Joe is doing is taking the original 10 by 12, he's adding on x feet this way, x feet this way. The new width is 10 plus x, and the new length is 12 plus x. So we now know that if I take the length times the width, it has to be 180, and that was choice B. They don't even solve the problem. They want you to just set it up and leave it that way. Okay? There are more problems with Pythagorean theorem. You can do a rectangular frame problem. I haven't seen too many of those on Regents exam, but certainly that patio question would be appropriate. Okay, so I think that takes us through, there's another frame problem where you're increasing things. Let's just leave it with that, okay? We got through everything tonight, which I'm really pleased with. Next week we'll be looking at coordinate geometry with slope of straight lines and also functional notation. If you have problems or questions, please bring them in with you, and we'll see what we can do to make you feel more comfortable about getting through this exam. You've got almost a month or a good 3 weeks to practice on this, and hopefully you'll feel much better by the time we're finished with everything. So thank you so much for coming tonight.
Expert teachers and educators at Learn America have created an online platform that helps students better prepare and improve performance in standardized tests in math and science. Step 1. Our unique methodology involves taking pre-assessment tests. Students take pre-assessment tests to determine their skills, knowledge, and readiness required for taking a course. Students are provided a detailed progress report at the end of the assessment to determine their strengths and weaknesses, and areas to focus on in order to achieve higher success in the course. Students access the courseware through the Learning Management System, or LMS, that is available anytime, anywhere, either through a browser or through the apps for the Android or iOS platforms. Students will have direct access to instructors, view any posted course announcements, and view a calendar of upcoming course events such as homework due dates, assessments, and so on. They may also download a learning report detailing any of their course activity, such as assessment scores, anytime. Step 2. Personalized learning plan developed based on the student's test scores in the pre-assessment test. The LMS includes an ebook for each course that provides theoretical concepts broken down by chapters and topics. Each chapter includes diagrams, graphs, or animated videos to provide visual demonstrations of the theory. The LMS platform has several features to make the learning process easy. Students can highlight important information, take notes, use the online calculator, and unit converter. Our expert teaching staff has created an extensive question bank that provides self-assessment questions in the form of quizzes after every chapter. These tests provide students a quick assessment of what they have learned in each topic or chapter. Students get to view the results immediately and provide an instant view of what specifically needs to be revisited prior to moving to the next topic. Step 3. Adaptive assessments and formative updates, where students then experience a series of assessments. Formative assessments are configured to reinforce the essential concepts behind major topic areas and to prepare students for more rigorous assessments as they march towards exam readiness. The assessment results allow students a full 360-degree view of the courseware to reinforce the learning, and step-by-step detailed solutions to reinforce problem-solving abilities. Faculty will use the formative assessment results to further guide the students. The students are then put through a more challenging adaptive assessment process. Much like progressing through a video game's levels, students climb the competency ladder by mastering one concept at a time. The adaptive assessments culminate in a mock final exam covering the complete course. Step 4. Interactive moderated online forum. Students get an opportunity to participate in online discussions. Here, they can post questions and share information with other students taking the course, as well as faculty and teaching assistants. Step 5. Progress report and intense interactive review dialogues. We provide a detailed, personalized progress report to view course progress. Students may participate in faculty-led review dialogues. This is conducted either in person or over an online conference. Step 6. Ready review. Towards the end of the course, as their test approaches, students take a final summative assessment that details specifically what sort of outcome they can expect from their exam. With this assessment, students can dig deeper into what they need to know. Practice exams are available anytime